Welcome to this first colloquium of the season. Speaker is our very own Matthias Rempel. Matthias received his PhD in astrophysics in 2001 from the University of Göttingen. And sorry, I was trying to go get the pointer, I was catching my breath. And the following year, he came to HAO as an ASP postdoc visitor and has been a scientist since 2004. His research focuses on theoretical modeling of the solar interior and solar photosphere, including structure of the overshoot region and magnetic flux storage, origin of penumbral fine structure, subsurface structure of the sunspots, flux emergence and sunspot formation, and quiet sun magnetism. And he has received numerous awards, including the Otto Hahn Medal in 2003 from Max Planck Society, and more recently the Harvey Prize in 2011, and the UCAR Distinguished Achievement Award in 2012, all for his groundbreaking works on 3D sunspot simulation. And Matthias.
Okay, thank you very much for the introduction. So the talk today is about quiet sun magnetism. There will be no sunspots in this talk. I will talk pretty much about everything else in the solar convection zone. If you look at the sun, even during an active day, most of the surface of the sun is covered by something which is called quiet sun. And if you estimate the total amount of unsigned flux which is found in these regions, it's a few times 10 to the 24 Maxwell at any given time. And this is comparable to the flux which is emerging in form of active regions throughout an 11-year cycle. So in terms of total flux content, the quiet sun is actually quite significant. And of course, this number depends very strongly on where you measure it. If you go further up, this refers roughly to the tau equal 1 level. If you go higher up, this can easily drop by 1 order of magnitude. But if you just go a few megameters beneath the surface of the sun, these unsigned flux content easily increases by 1 or 2 orders of magnitude. So it's a substantial amount of flux hidden on small scales. And on the right side, I show here a result from small-scale dynamo simulations I will be talking about here. And this is really an enlargement of a patch which is so small that I couldn't even draw here the rectangular box. This is done at a resolution of 2 kilometers, which is kind of the highest resolution we can afford today in numerical simulations. The question I mostly want to address in this talk is, where does this quiet sun field come from, and what does it tell us about the solar dynamos? How strong is the quiet sun magnetic field, and how do we know this? Some of the best observations we have are Hinode observations, and I just show here 2 numbers which were derived by different people, looking at slightly different snapshots, doing slightly different processing in terms of including network field in the one case or still keeping it in the average. But typically these numbers are of the order of 10 Gauss, which is a weak field. But most of these magnetic field is organized on very small scales, so we have a lot of Zeeman cancellation. And if you really want to know how strong the quiet sun field is, you have to do forward modeling using a high resolution MHD simulation and see how much field you have to put in there so that after you did all the forward modeling of spectral lines degradation to the observation, that you actually match up with these values. And this was done in this 2010 paper, and they estimated roughly something in the 6380 Gauss range. And this corresponds to an RMS field strength of about 200 Gauss, which is 30% of the equipartition value at the tau equal 1 level. So by those measures, it's already a fairly strong field. And this just shows how this match was done. Here the very thin black line is a PDF from Hinode, and here these are different simulations in different domain sizes with different field strengths. And depending on which part here you want to fit, you see it's roughly a 60 to 80 Gauss you need at the tau equal 1 level to match the observed PDF. what are the open questions? How is the magnetic field distributed in the quiet sun? And distribution, I mean spectral energy distribution. Is there any preferred scale? Sometimes you read that some people think there's a preferred scale for flux tubes around 100 kilometers. What is the strength distribution? What is the fraction of kilogauss field in the quiet sun? Is all the kilogauss field you see on the solar surface network field which is related to active regions, or does the quiet sun itself produce kilogauss field? What is the distribution of inclination? How much horizontal field is there? And where does this field come from? The two possible scenarios are remnant flux from active region decay. On the observational side, there's only very weak indication for this process. Bruce Lights looked at this and found only a very weak dependence of the strength of the quiet sun field on the net flux imbalance in the network surrounding quiet sun patches. There's also only very little evidence that the quiet sun field strength varies throughout the solar cycle. The other scenario is a small-scale dynamo, but there are also theoretical challenges here. We have several small-scale dynamo models, but many of them fall short by a factor of 2 to 3 compared to the observed quiet sun field strengths. And the very big challenge for any MHD simulation on the sun is that the sun has a very low magnetic Prandtl number, which means that the magnetic Reynolds number is much smaller than the fluid Reynolds number, but both numbers are very large at the same time. And I will address this problem here through magnetoconvection simulations in the photosphere. They are driven by radiative transfer, so these are simulations which, at least to the best of our knowledge, include all the relevant physics. The small-scale dynamo problem has been addressed for more than 15 years in 3D simulations. The first ones were incompressible. Then people started to at least include compressibility in the inelastic approximation. The first realistic MHD simulation of the solar photosphere with radiative transfer was done in 2007 by Alexander Vögler and Manfred Schüssler. They focused on the uppermost few megameters of the convection zone, and they could show that you can get a dynamo despite the fact that you have extremely little recirculation of plasma in the photosphere. Most of the mass comes up in the photosphere, turns over, and disappears. If you want to keep a dynamo alive, you need at least some recirculation. But as I mentioned before, these simulations, it fell short by about a factor of 2 to 3 compared to observations. So what is really the challenge on the modeling side? One problem is the question, how strongly is the photosphere coupled to the rest of the convection zone? We cannot simulate the full convection zone, including the photosphere and the base of the convection zone. So there's always an issue with the bottom boundary. The other problem is how to deal numerically really with the regime the sun is operating in. And No, this is the field strength in simulations fall short of the observed value by a factor of 2 to 3, which is a lot in terms of energy. The other challenge is how to deal numerically with the low Prandtl number regime. So the approach I'm taking here is I use mostly simulations with open boundaries, but I allow for both vertical and horizontal field, which essentially means I assume a deep convection zone which is magnetized. And I come back to these boundary conditions, and that is actually one of the key parts of this investigation. The way I deal with the low Prandtl number regime is I use here a large eddy approach, which means I only focus on, I try to focus on the well-resolved scales and try to minimize the diffusivity as much as I can without risking numerical instability. This means that you can reach fairly high magnetic and fluid Reynolds numbers, but the Prandtl number stays close to 1. And I also come back to the Prandtl number issue towards the end of the talk. I cannot cover all the details here, in particular the details of the numerics, but I refer you to this paper which came out a few months ago if you want to read those. In my simulation setup, I try to explore 3 things: the domain size, the grid spacing, and the bottom boundary condition. I mostly talk here about two domain sizes. One is a granular size domain, 6 megameters wide, 3 megameters deep. The photosphere is about 700 kilometers beneath the top boundary. And I use a mesogranular size domain, about 25 megameters wide and 7.5 megameters deep. The top boundary is here 1.5 megameters above the photosphere. Grid space I explore from 32 down to 2 kilometers. And everybody who does 3D simulation knows that the computation time goes with the fourth power of your resolution. So if you actually try to simulate the same simulation with 32 and 2 kilometers, there is about a factor of 100,000 in computing time between these two simulations. So this really, of course, I didn't run the 2 kilometer resolution run as long as a 32 kilometer resolution run. And I explore the bottom boundary condition. I look at open boundaries with different assumptions about the field in inflow regions, but for comparison, I also looked at closed boundaries. They are not the sun, but they are a much better defined dynamo problem because all the plasma recirculates inside your domain. All the dynamo processes are contained inside the domain. The simulations, they start from a very weak random seed field of the order of 10 to the minus 3 Gauss. So why do I explore these things? As I mentioned, I use here something which is called realistic MHD simulations. They're realistic in terms of their physical ingredients, compressible MHD, realistic equation of state, and 3D radiative transfer. But we have only limited computing resources. We cannot simulate the whole sun, which means we are influenced by boundary conditions. We can only simulate a finite time interval. So the initial condition matters. And we can only afford a finite resolution, which means that the treatment of unresolved scales and resolution dependence is important. Most problems are impacted by all three limitations. The small-scale dynamo problem doesn't care too much about the initial condition, since I start from a very weak random seed field and you get a very fast initial kinematic growth into the saturated state. But boundary conditions, and related to this also the domain size and the resolution are important. And because of this, I would like to say here that even the most realistic MHD simulations we can do, they are all numerical experiments where you explore how your outcome depends on all these factors. Since I talk a lot about small-scale dynamos, just a very, very brief summary what a small-scale dynamo is. If you're operating in the high magnetic Reynolds number regime, you have the ideal MHD, where the time derivative of B is given by the curl of V cross B. You can use some vector identities to transform it into this equivalent expression. And if you now replace the divergence of the velocity field through the equation of continuity, you can write this in an even more compact form, which is the Lagrangian derivative of the quantity B over rho is given by the shear of the velocity field in the direction of B over rho. Now, if you take any fluid and you trace Lagrangian particle paths, you essentially integrate the velocity field. You can do this for 2 points in your velocity field, x1 and x2. And then you focus on the separation of these two particles in your velocity field, which are initially separated by a very small distance. And you derive an equation how this separation evolves in time. And mathematically, this equation is identical to the induction equation, the ideal induction equation. If you have a chaotic flow, this separation grows exponentially for very small initial separations, which means if you sprinkle a very weak magnetic field into a chaotic flow, you also would expect an exponential growth due to the mathematical similarity. Of course, I neglected here the magnetic diffusivity. So in reality, this only happens if your magnetic Reynolds number is high enough or your magnetic diffusivity is low enough. Typically, the Reynolds number has to be of the order of 100, a few hundred. In the photosphere of the sun, the Reynolds number is about 10 to the 5, and it increases as you go deeper into the solar convection zone. So how do these simulations look like for the solar setup? Here I show the kinematic and the saturated phase of a dynamo simulation in the 6 by 6 megameter box. I show here the intensity, the vertical velocity, plus minus 5 kilometers per second, and the field strength during an earlier phase and a later phase. As long as the dynamo is in the kinematic growth, the magnetic field is organized on the smallest possible scales, and it's mostly found in the downflow lanes where you have the strongest shear. But as the field becomes stronger, the field becomes organized. It's still mostly in the downflow lanes, but you see much larger scale structures. You see, for example, here these sheet which has the same polarity and stretches over 1 or 2 megameters. So the scale of the field depends strongly on how strong the strength is. And the difference between these snapshots is, in this case, the Lorentz force has a significant feedback on the flows. In this case, it's purely kinematic. And here the field strength also becomes strong enough that you start seeing some bright points showing up in the downflow lanes. This is 4 kilometers resolution in this case. So there are 1,500 grid points across. Now, if you look at this in terms of power spectrum and probability distribution functions of field strengths, in the kinematic growth phase, the power spectrum of magnetic energy peaks here on a scale which corresponds to something like maybe 30 kilometers, which is something like 8 grid spacings. This is close to the smallest scale you can possibly resolve. And the blue line is the kinetic energy spectrum for that case. As the field grows, it reaches the super equipartition state on these small scales, and the power spectrum has no defined peak. It kind of flattens out towards the larger scales. And the kinetic energy becomes suppressed by roughly a factor of 2 on the small scales. If you look at PDFs, initially, if the field is weak, they're mostly exponential, but as the field becomes stronger, you start forming a bulge here. I think the battery dies here. You need some laser pointers with a self-sustained dynamo to avoid this problem. Yeah. As the field becomes stronger, you start seeing a bulge here towards kilogauss field. And this is, of course, related to these bright points also forming up in the photosphere. How does this all depend? First, I show a movie, actually, of the saturated state of the dynamo. This shows the intensity, the vertical magnetic field at tau equal 1, and the bottom panels show in a cut through the center of the domain the field strength and the inclination of the field, and red is horizontal field, whereas blue is vertical. And you see that most of the magnetic field becomes organized in very thin sheets. Sometimes you see alternating polarities very close nearby. And then there are no clear, distinct flux tube-like features. Typically, these brightenings here, they are just concentrations which show up along these fields. They're just temporarily showing up, and at a later point, they just fall apart again.
Can I ask a question?
Yeah.
Is there an implication that the magnetic field distribution in the upper right is similar to the velocity?
I mean, you find most of the strong field in downflows. And I mean, that gives you this very similar appearance. Yes.
Thank you.
Now you can ask, how does this actually depend on resolution? Here I show the simulations which vary by a factor of 16 in resolution. I ran the 32, 16, 8, and 4 kilometer resolution case from a weak seed field. The 2 kilometer case, I think this one is also close to that. The 2 kilometer case was restarted from the 4 kilometer case. And here I compare the power spectra of kinetic and magnetic energy for all these cases. And now the field strength fluctuates in these small boxes. And the comparison, the way I did it here is I averaged snapshots which had roughly the same unsigned flux of 80 Gauss. So I averaged between 75 and 85. So in this run, I compare simulations or snapshots which had roughly the same amount of magnetic field in the photosphere. And because of this, you see in the lowest resolution case, the power on the small scales is a little bit enhanced because you don't have enough room in spectral space to distribute the energy. But once you have 8 kilometers resolution, it kind of becomes converged on the large scales, and you just add more and more small scale features. This shows the ratio of magnetic to kinetic energy. And once you have a resolution better than about 16 kilometers, you start seeing this super equipartition regime, and there's some indication that you might have a more or less constant ratio of a little bit more than 2. This is at tau equal 1. If you go a little bit deeper in the convection zone, this ratio changes. But factor of 2 is roughly found everywhere. Here I show the PDFs for the field strengths for horizontal and vertical field, and there is some realization noise if you look here at the tails of the distribution, where you only have a 10 to the minus 7 occurrence rate. But overall, the PDF is essentially resolution independent. So these solutions, they look very converged, but the convergence doesn't necessarily mean they're correct. The question is, are they really converged towards the correct solution, which would be one which is computed with the realistic viscosity and resistivity. And these simulations are done with the implicit Prandtl number of 1, where the sun has a photosphere, has roughly a Prandtl number of 10 to the minus 5. And this is a question I cannot answer at this point. There are two ways to answer this question. The one is at some point comparing them to really high resolution direct numerical simulations with realistic diffusivities, or using high-resolution observations to confirm that, at least on these scales, you can observe that this agrees with the observed sun. Here I look at the energy distribution of the photosphere in a slightly different way. These are integrated power spectra and integrated distribution functions. So I take this power spectra, I integrate the energy from the largest scales going to the smallest ones, and I integrate the energy from the weakest field going to the strongest one. And this tells you roughly how the energy is distributed. In the spectral space, you find that about, at least for the highest resolution case, about 50% of the energy is on scales smaller than 100 kilometers. And you also need a high resolution, 8 kilometers, I would say, even better than this, if you really want to get the spectral energy distribution in the photosphere right. What you also can estimate from this plot is if you're observing the sun with something like Hinode, you can see up to 20% of the magnetic energy which is present in the photosphere.
By high grid spacing, you mean low grid spacing?
I mean, yeah, low grid space.
Yeah,
oh, yeah.
You mean high resolution?
Yeah, high resolution, but low grid spacing, yes. Thank you. Okay. Yeah, so you need at least 8 kilometers resolution or better to resolve the spectral energy distribution. Hinode would see something like 20% of the energy. With something like the DKIST, if you're lucky, you can see 90% of the energy. So that's a big step forward. In terms of the field strength distribution, about 50% of the energy comes from field which is weaker than 500 Gauss. And since the PDF didn't have a big resolution dependence, there's also no big resolution dependence of this property. But of course, it depends on the field strength. Here, the blue dotted line had 60 Gauss instead of 80 Gauss unsigned flux. And the dashed blue line is also a 60 Gauss case, but it's actually in the mesogranular domain. If you have a bigger domain, this changes a little bit the energy distribution. You get more contribution actually from kilogauss field. And this is now just showing two pictures with a zoom in. The highest resolved simulation I have done, this is at 2 kilometer grid spacing. You see several very small bright points here, and I zoom in here into this square to highlight 3 bright points, and then I can toggle back and forth here with what actually the vertical field distribution is in both cases. You see that most of these bright points are more or less unipolar features, but they're kind of embedded in a background of more sheet-like features with strongly alternating polarities. So talking about bright points, what is the filling factor of kilogauss field in these simulations, and how does it depend on resolution and the overall field strength in the photosphere. Now, as I mentioned before, all these simulations start from a very weak random field. So what I did here, as the simulation went through the kinematic growth phase and the field strength was increasing, I looked how the filling factor of kilogauss feet changes as function of the average vertical flux density in the photosphere. And you find that roughly to 30, 40 Gauss, not much is happening. But once you exceed that threshold, the filling factor of kilogauss feet goes up. And for the values which are typical for quiet sun, it's something like 0.2 to 0.4%. So it's still a small number.
Matthias, maybe you could mention this, but is there a critical field strength at which it might perform?
I mean, I do not know really from observations, but what you find, for example, if you plot in these simulations the brightness as function of the field strength. So as the field strength is growing, you first see actually decrease, which is simply the effect that most of the magnetic field is in downflow lanes, and they are darker. But then once you go beyond kilogauss feet roughly, then you finally get again above the average brightness you have in that snapshot. And there is some scatter here, but overall there is no strong resolution dependence, and this is also what I showed before. The PDFs don't really depend on resolution. But there's one quantity this depends on. This is a simulation, same setup, but this was in the mesogranular domain, a wider and deeper domain. In that case, you find for the same field strength roughly twice as many. The filling factor is twice as large for kilogauss field. And the small domain is shown here in this corner. The big domain is the plot here. And as you increase the domain size, the magnetic field becomes organized on larger scales. In this case, these are mesogranular scales, since the domain doesn't allow for any larger scales. And you see overall more longer-lived strong field regions, which increase overall the amount of kilogauss field you find in the photosphere.
So, can you guess what happens if you would make this calculation on 2D supergranular scales, which would be the next?
I mean, we have done that, and the number goes up, but the problem is, as you make the simulation boxes much bigger than the supergranular scale, the larger scales are wrong compared to the sun. You overestimate power, and that influences also the distribution of magnetic field. You roughly get it right to the scale of supergranulation. That's the work Jesse Lord did. But once you go beyond that scale, I wouldn't trust these simulations too much. And this is a general problem. All convection simulations we have for the sun, they seem to overestimate convective velocities on larger scales. And that, of course, feeds back at some point in these field strength distribution. What I can say is I looked at this in a 100 megameter wide domain, and this filling factor went up to roughly 1%. But if you go to bigger domains, you start screwing up the larger scales, and I wouldn't trust that result necessarily that much anymore. Now, if you now compare the power spectrum and PDF for these two simulations, you see that increasing the domain size increases the power on the large scales, and it increases the fraction of field starting from something like about 750 Gauss. You see an enhanced tail here in the PDF, which translates into this increased fraction of kilogauss field. But in none of these dynamo simulations I've done, you see an indication that you might get a secondary peak in the PDF. You have to add a net flux to the box, more than 30 Gauss, and I will show this a little bit later. This is about the magnetic field inclination in the photosphere for simulations which had different field strengths. I plotted here the ratio of horizontal to vertical magnetic field as function of height. The photosphere tau equal 1 is here at 0. In the deep photosphere, for all field strengths, it's close to isotropic. square root of 2 here corresponds to isotropic field strength distribution. But you see a peak of the ratio of horizontal to vertical field about 400 kilometers above tau equal 1. And the peak itself is strongly field strength dependent. Weaker field has a stronger peak because the field is organized on smaller scales. You have more low-lying loops which close deep in the photosphere, which enhance the horizontal field here. A stronger field is more vertical and extends higher up above the photosphere. And for quiet sun values, I would expect here something around 2 to 3, depending where you look. People have looked at this with Hinode. Original analysis of data had the values as far as high as 5, but more recent papers I have seen, they brought it down to 3. There's a lot of noise involved in measuring the horizontal field component, so it's challenging to measure this feature. But as it turns out here, the height where this happens seems to be very robust, but the value of the peak is strongly field strength dependent. And here I just show the PDF of the inclination angle with respect to the vertical for the deep photosphere averaged in this height range and in 400 to 450 to 500 or 450 kilometers height are the dashed lines. The black solid line here corresponds to an isotropic inclination distribution. So the deep photosphere is close to isotropic.
There are different field strengths here. Are those different phases of the growth?
Yes, it's the same, yes. So there might be also some time evolution issue always convolved here, but I also have a 30 Gauss case here which actually saturated there, and it pretty much agrees with this.
Is your tau equal to 1 surface something where you're tracking?
Yes,
tracking
yeah.
I understand this in terms of, if you have a sunspot, your field inclination should be 0, right? Because
In the center of the umbra, yes, yeah.
so at what point in your simulation you increase the field strength, would this preference show up?
I mean, zero field you are most likely to find if you look in the network where you have a strong kilogauss field, and right in the center of this, you're most likely to find 0. But this is an average of the horizontal field and the unsigned vertical field over the entire box, and it takes a ratio of the two.
So you're saying you have to have really a lot of flux in there for this to sort of go towards a preference of no inclination at tau equals 1.
I mean, at tau equal 1, regardless of the field strength, it stays close to isotropic in all cases. But if you go 400 kilometers above tau equal 1, where you observe, I mean, at least in the simulation, where you find most of the horizontal field, actually, if you look at the field strength of the horizontal field as a function of height, you see even a secondary peak there. And this peak depends strongly on the field strength. And that has to do with the organization of the field. The stronger the field, the more power you have in large scales. And this corresponds to field structures which reach higher up into the atmosphere. And then you have less loops lying in the deeper part of the atmosphere which close and contribute to the horizontal field.
So then these peaks refer to more vertical.
No, this is more horizontal field here. This is the ratio of horizontal to vertical. Yeah.
Does this mean that the record of longitudinal magnetograms started by HAO, measurements in the quiet sun, what's the implication of this? Do we have to multiply those numbers by 3 to get an estimate of what the unsigned flux would be in the quiet sun?
I mean, it depends really where you measure. If you measure here, you have most energy in the horizontal field.
Yeah.
But if you measure really in the deep photosphere, isotropic field distribution is a fair assumption. So each field component contributes roughly the same. So you multiply it by a square root of 3. Now this is now one of the most important parts here, the role of the bottom boundary condition. These are all very small boxes compared to the size of the convection zone. So, and these are open boundaries which allow for mass and magnetic field to leave the domain. And the problem of open boundaries is you have to make assumptions about what's coming back in. And here I made different assumptions about this, the most extreme ones. I compare here two boxes with different depths. This one is a little bit more than 2 megameters deep. This one a little bit more than 6 megameters deep. You see two solutions which are here on the lower branch with weaker field. Two solutions here, actually 3 solutions in the middle, and these are just extrapolations I will mention soon. Now these lower branch solutions, I made the most conservative estimate you can do. You just set the magnetic field to 0 in inflow regions. You assume the rest of the convection zone has 0 field. You essentially constrain the dynamo to operate only in the part of the domain you really simulate. All these solutions, they reach an unsigned flux of about 30 Gauss in the photosphere, and it doesn't really seem to depend where you do this. If you increase your domain depth by almost a factor of 3, use the same boundary condition, the photosphere, you reach the same. These are solutions where I allowed for horizontal field in inflow regions, so they kind of assume the rest of the convection zone is magnetized. These are solutions which reached about 60 Gauss, which is very close to what the quiet sun is doing. And I also added here an even deeper domain solution which went to 18 megameters depth, and they all agree fairly well. And then these dotted lines here, these are solutions where I rescaled the RMS field strengths, which are here. These are the RMS field strengths values such that the RMS field strength increases with depth at the same rate as the equipartition field strength, which is a measure of the kinetic energy available. And the solid lines here are the equipartition field strengths. So these are solutions in which asymptotically you reach equipartition in the deep convection zone. They correspond to values of about 85 Gauss unsigned flux in the photosphere. It's here, I mean, it's of the order of about a little bit more than 1,000 Gauss in this box. So what I did is just a mirror boundary condition. I just mirror whatever is inside the domain into the Gauss set. So I kind of let the field strength loose to do whatever it wants to do. I mean, you can discuss whether this is a meaningful boundary condition. Likely it's not. But what I really want to do is I want to explore how much it matters. Normally, you really like to be in a regime where the boundary condition doesn't matter. In this case, it really matters, but it also tells you something about the problem.
So could you reinterpret your mirror boundary condition? What is the strength of the field that you're then allowing to come in?
It's basically, I mean, it's roughly half of the RMS what is here. That is roughly where it settles. I mean, the horizontal, it's mostly dominated by vertical field here, which really doesn't contribute to the pointing flux in inflow regions. The horizontal field is typically a little bit less, but here where you have something like 2,200 Gauss RMS field strength, the horizontal field, which is at this boundary, is about 1,000 Gauss. But it's really here only exploring what is the range of possible solutions depending on what the rest of the convection zone is doing. If the convection zone is magnetized at equipartition, you get 85 Gauss in the photosphere. If you assume the convection zone is free of field and you only have a dynamo operating the uppermost 2 megameters of the convection zone, you get 30 Gauss, which is half what is observed. So the observations are around 60 Gauss, which is a little bit less than equipartition, but still a substantially magnetized convection zone. Now, what I wanted to discuss here is what is actually the potential contribution from active region decay. So far I only talk about small-scale dynamos which had no net flux. Here I did some simulations where I did a small-scale dynamo, but I added net flux to it. And this is more Plush-like. This is a weak Plush, a strong Plush of 30 Gauss, 120 Gauss. And then I looked again, how does this actually influence the distribution of magnetic energy and field in the photosphere? most of the energy, so the solid line is the small-scale dynamo without any net flux, and I added 30, 60, 120 Gauss to it. Most of the energy goes on the large scales because there's most room for it to go. If you look at the PDFs, you see this secondary peak showing up here at somewhere 1.5 kilogauss, which happens once you have more than around 60 Gauss net flux in your simulations. At the same time, the opposite polarity flux is suppressed in the PDF for the vertical field. That is a filling factor issue. Most of the strong field is found in downflow regions. In these simulations, you fill up most of the downflow regions with the imposed net flux. There isn't really much room for the strong opposite polarity field to be present, so this part is suppressed. But the most interesting thing is that, for example, if you look at the PDF for the horizontal field, which is, in this situation, we have a lot of net flux, the most unbiased measure for the mixed polarity component of the field, that doesn't really change much at all. Actually, for the 120 Gauss case, it increases by about 15%. So if you really talk about something like quiet sun, where you might have 10 Gauss flux imbalance, this would be an effect of in the percent range. So it's a weak effect. So what you can conclude from this is that if you add the net flux imbalance to these simulations, you have a strong modulation of the network field, which shows up here, but you have essentially no influence on the mixed polarity field. In particular, if you look at fields less than 500 Gauss, which provides 50% of the energy in the quiet sun, there's no change at all.
Yes, how did you accomplish this? By injecting more flux in the bottom? Or?
No, you use the same boundary condition, but you just started the simulation. I just added 120 Gauss mean field to it, to the saturated dynamo, and I ran it for several convective turnover time scales.
Vertical field?
Vertical, yes. Since it's a periodic box, you have to add the same amount of flux at every height. And what you see here is mostly a consequence of stratification and a very small recirculation in the top few megameters of the convection zone. The net flux is swept into the downflow lanes, but then it's stuck there. It has very little means to feed back on the inter-network regions. Now, what does this all tell us? The bottom boundary condition parameterizes how the photosphere is coupled to the rest of the convection zone. And what it really, the question is here, how much magnetic field is transported upward in convective upflow regions? Hinode observations, they indicate that the quiet sun is something like 60 Gauss, and this implies you only can get in this simulation a value of that strength if the rest of the convection zone is magnetized close to equipartition. In that sense, the observed quiet sun field is the tip of the iceberg of a rather strong and dynamically relevant field throughout the convection zone. Small-scale dynamo just restricted to the photosphere is not enough. It would saturate about half the observed field strength. You need small-scale dynamo action throughout the convection zone over a wide range of scales. This means that the small-scale and large-scale dynamos are inherently coupled with each other, and the magnetic field shows the organization over a wide range of scales. The photospheric quiet sun field can be modulated by two processes in strength. The one is a flux imbalance, which can come from active region decay. This seems to be a very weak effect. It mostly influences the network. The main effect is the convective pointing flux in upflow regions. And this can be a strong effect, more than a factor of 2, at least if you explore the full range of extremes in the boundary conditions. I skip this one. If I have a few more minutes, this is a little bit more convolved part of the talk. I would like to talk a little bit how the energy transfers in these dynamos work in detail. And I have to introduce here one concept, which is that of an energy transfer function. So assume a very simple equation of the form: you have a time derivative of the velocity is some forcing f, and I assume the density is 1. Then you can look at the spectral energy density, which is here the power of the Fourier transform of the velocity. And you can look how this quantity evolves with time. You take the time derivative of this. And then you can, and what you end up with is here a term where you Fourier transform your force and multiply it in Fourier space with the Fourier transform of your velocity. So basically you ask how much energy is converted by this force at a certain wave number in Fourier space. And you can do this for all terms in the momentum equation, and you get energy transfers into the energy reservoir of kinetic energy. You can do the same for the induction equation. You get energy transfers for the magnetic energy reservoir. Just a technical detail, since the system is stratified, I do only Fourier transforms in the horizontal direction, which means you don't properly account for energy transfers in the vertical direction here. And I want to look at this to discuss how this dynamo is actually saturating. Here on the left panel, I show how the power, basically the power spectrum of the vorticity changes between the kinematic and saturated state and the power spectrum of the divergence of the velocity field. Solid lines is the kinematic state where Lorentz force feedback is weak. Dashed lines is the saturated state. And you see a reduction of the shear, and you see a reduction of the divergence, mostly on the small scales, but overall this reduction is rather moderate. It's not enough to really saturate the dynamo. What you then can look at is you can look at the energy transfers which come from the shear term in the induction equation. And what you see there is the shear, which is mostly related here to the curl of the velocity field, that actually drops by more than an order of magnitude as the dynamo is saturating. In the same way, if you look at the compression term, which is related to the term in the energy equation, which is related to the divergence of the velocity field, that term actually, it drops a little bit, but not too much. So these dynamos, they mostly saturate through a misalignment of magnetic field and shear. Whereas the compression term doesn't really change much despite some change of the divergence, since the magnetic field has very little way to misalign actually with the divergence of the velocity field. In this term, you can get a lot of misalignment by having the direction of the magnetic field in the direction of maximum shear orthogonal to each other. And you can also have a misalignment where the induced field is misaligned with the magnetic field, which is already there. In that case, you change the direction of the field, but not the energy. And these misalignments bring down the induction by shear substantially, despite only a moderate change of shear. The compression term is very difficult to quench, since the only way you can quench this is by either reducing the divergence of V, some of that is happening, and by decorrelating the magnetic energy with regions of divergence of velocity field. But this is against the nature of magnetic field. Most of it is found in downflow regions which have convergent flows. What this means is that the dynamo saturates mostly through shear, while the contribution from compression actually stays the same. So in the saturated state, actually the compression term becomes much more important than it is compared to the kinematic state. No, I mean, this was just an example to explain what this transfer function is, but you apply this to the momentum equation. So this can be the Lorentz force, it can be pressure buoyancy driving, all the terms which are in the momentum equation. Or you can apply this to the induction equation. In that case, this F, for example, is a B grad V term. So what this term tells you is how much energy is added or taken out, for example, of kinetic energy by the Lorentz force at the wave number k. But the Lorentz force can result from magnetic field over a wide range of scales. And this energy is put over a wide range of scales in the magnetic energy reservoir. This is the transfer functions due to stretching, B grad V, and this is the transfer functions due to compression, and I normalize them by the magnetic energy to have them in terms of a dimensionless shear rate. And it's mostly the stretching one which gets suppressed, whereas the transfer by compression stays pretty much the same. There's some reduction on the large scales, but the small scales stay pretty much the same.
Solid and dashed curves are.
Solid is the kinematic phase, dashed is the saturated state. And of course, these features here, they are in the range where numerical diffusivity really matters a lot in your dynamo. Not necessarily. I mean, if you really look at the alignment of flow and velocity field, it's not that good. It's really more misalignment of the magnetic field with the gradient of the velocity field. But one important point is the reduction of shear and divergence itself is not large enough. This is mostly something which has to do with the relation of magnetic and velocity field with respect to each other, but not the reduction of shear in absolute terms. And I think I'm kind of running out of time here, so I might want to skip over that part and want to talk about one more point, and that is the power or the efficiency of the dynamo. And if you take these simulations and compute something like the work converted by the Lorentz force, that is, in these simulations, about 50% of the available pressure buoyancy driving, which is a lot. And because if you integrate this over the top 10 megameters of the convection zone, that accounts to about a solar luminosity. This is just the top 10 megameters of the convection zone. This is the rate at which energy is converted by the small-scale dynamo. And important to note is this is not an energy sink. This is a conversion rate. The energy is converted by the Lorentz force into magnetic energy, is then dissipated. If the dynamo wouldn't be there, the dissipation would be handled through viscosity alone. But this is a fairly large number. If you estimate how much a large-scale dynamo might convert, for example, through the energy extracted from the mean shear of differential rotation, this is more % of a solar luminosity. So in terms of this energy conversion rate, the small-scale dynamo is actually more powerful by 1 to 2 orders of magnitude. But it's, of course, difficult to draw exactly the line. Where does the small-scale dynamo start and where does the large-scale dynamo begin? But why is this only 50%? And this is something which is related to the magnetic Prandtl number. These simulations have a Prandtl number of close to 1. The energy dissipation is in 50-50 between viscosity and magnetic diffusivity. And this is something which was found before by Axel Brandenburg, where he looked at the ratio of kinetic to magnetic energy dissipation as function of Prandtl number for large-scale dynamos and small-scale dynamos. And this ratio becomes larger if you increase the Prandtl number, which means in a high Prandtl number regime, most of the energy is dissipated through viscosity. In a low Prandtl number regime, where the sun is operating, most of the energy is dissipated through magnetic diffusivity. And I also did here experiments using my approach by trying to change the Prandtl number by using different numerical schemes for magnetic field and velocity field. And here in this plot, I show as function of height the horizontally average pressure buoyancy driving in the system, which is these dashed lines here. There's a peak right beneath the photosphere. Most of this energy goes into acceleration of fluid. And then I showed for runs which had different Prandtl numbers, the net energy converted by the Lorentz force. In the high Prandtl number run, this is rather low, whereas in the low Prandtl number run, at least in the deeper layers, that becomes close to 100% of the available pressure buoyancy driving. Now, I think I don't have the time to go in detail, but what is a little bit surprising here is that actually a run which has a stronger field has a smaller amount of energy transported by the Lorentz force. And what happens here is all these simulations, on the large scales, the Lorentz force extracts roughly the same amount of energy from the velocity field. What happens in the large Prandtl number case is that most of this energy is returned on small scales to the kinetic energy, where it is immediately dissipated through viscosity. So what this means is the larger diffusivity is responsible for most of the energy dissipation. The energy transfer on large scales is independent of the Prandtl number, and the energy transfer by the Lorentz force near the scale, which is the maximum of the resistive and viscous scale, is Prandtl number dependent, and this facilitates the energy exchange. And this means that the net exchange is highly Prandtl number dependent. So if you look at the different regimes, in the high Prandtl number regime, the dynamo is mostly an energy transport mechanism from large to small scales. And the kinetic energy cascade is replaced by a magnetic energy cascade. This is not purely magnetic because you cannot transport energy without having some velocity field involved. If you have a very low Prandtl number, the dynamo, but still high Reynolds number, is maximally efficient, and it absorbs close to 100% of the available pressure buoyancy driving. And what it also means, energetically, the low Prandtl number regime doesn't really exist, since very little kinetic energy is left on scales smaller than the magnetic dissipation range. And what does this really imply for the large-scale dynamo? And this is kind of where I would like to end here. If the small-scale dynamo is close to 100% efficient, the large-scale and the small-scale dynamo have to compete against each other for resources. And this is an idea which I think was first pointed out in a recent paper by Fausto Cattaneo and Stephen Tobias, that in the high Reynolds number regime, a large-scale dynamo requires the suppression of the more efficient small-scale dynamo. And they demonstrated here that actually shear can suppress the small-scale dynamo and give room for a large-scale dynamo to operate. And the big question in the room is this all a technical detail or really of significant relevance for astrophysical large-scale dynamos? Or to phrase it this way, do we first need to get the small-scale dynamo right before we can get the right large-scale dynamo? Meaning a large-scale dynamo operating a very high magnetic Reynolds number. It makes simulations much more expensive, but we might have to explore this. Another side thought here is, if both dynamos compete, the absence of a large-scale dynamo might actually allow for a stronger small-scale dynamo. In that sense, the quiet sun might be actually less quiet during a grand minimum. Okay, and there I stop with this talk and just leave up here the summary slide with regard to the findings for the small-scale dynamo in the photosphere.
Nice talk. So you said the strength and orientation of the photospheric field depends a lot on the magnetic flux coming up from below.
Yes.
So can observations of the magnetic carpet give you some constraint on the low L structure of the magnetic field in the deep convection zone? If there was a lot of variation, spatial variation on low L's, would you see it in the photosphere?
I mean, one challenge is, you have a competition here of large-scale organized field emerging and field on small scales organized. The mixed polarity field, as it emerges, it roughly scales with a density to power of 0.3. It becomes weaker as it emerges into the photosphere. If you have a large-scale organized field, it roughly goes with the density to power of 0.5. That means you have to, if you want to increase the magnetic field in the photosphere through a large-scale organized horizontal field, you have to start with much more in the convection zone to get the same effect in the photosphere. But yeah, it might be possible, but it's this competition between small-scale and large-scale horizontal field which really both change the amount of mixed polarity field you have in the photosphere.
Gradients in the turbulent intensity.
Yeah.
Small scale flows.
One of my favorite questions would be, is there a hydrodynamic sun? Or in these calculations, are there, we're not measuring the magnetic field, would the surface convection look rather different whether you had magnetism or not?
So when I did some really high resolution hydro simulations of the photosphere, and you look in detail, granulation looks more rough. There's much more turbulent features and the edges which a little bit disrupt granules. Is that purely hydrodynamic? As you add a magnetic field, the granulation pattern becomes more smooth, and it looks similar to a hydro simulation which has been done with a much higher numerical viscosity. So in that sense, if there would be a real hydro sun, I would expect that granulation would likely look rougher than it is, but likely all the sun we have ever observed is a magnetic sun. So this is pretty hypothetical in that sense. But yes, you can see some evidence, but this roughness, yes, but also many of them are fairly diffusive. You really have to bring your diffusivity down quite a bit to get in this regime where you see an effect on the granulation in that sense.
Very nice talk, Matthias. In this concept, you speculate that the small-scale dynamo and the large-scale dynamo are most likely interlinked, inherently interlinked. So I was wondering how you would reconcile the surface transport and polar reversal in using this concept.
I mean, that is certainly mostly about the large-scale dynamo, and I mean, I haven't talked really about large-scale dynamo here at all. The only thing I wanted to point out that energetically, most of the energy transfers happen really in the small-scale dynamo, and it looks like that in the regime where the magnetic Reynolds number is high, but at the same time the magnetic Prandtl number is low, that the small-scale dynamo becomes so efficient that it takes close to 100% of the resources available. So a large-scale dynamo can only exist if the small-scale dynamo is partially suppressed to make energetically some room. And how that would change the way this large-scale dynamo is operating, I think it's an open question. This paper I pointed out here by Catano and Tobias is, to my knowledge, the first paper which pointed out this issue, that if you are operating in a regime where the small-scale dynamo takes already all the resources, that shear is not there to make the large-scale dynamo more efficient. It suppresses the small-scale dynamo in regions with strong shear and makes some room for a larger-scale field to emerge there. If this is just a technical detail or really changes the way a large-scale dynamo operates in the high magnetic Reynolds number regime, all the large-scale dynamos we have explored are very moderate Reynolds number, and in most 3D simulations which have large-scale dynamos, the small-scale dynamo is barely existent. I mean, it's an open question. But I just want to point out there is an issue here that we might have to think about in the future. But I mean, how that large-scale dynamo would look like that competes with the small-scale dynamo, I have no idea. I only looked here at the part of the small-scale dynamo.
May, or do I switch this on? I think it's on. So I think the most significant result here really is that you show that by observational evidence, the solar magnetism cannot be just due to small-scale dynamo action. There is an underlying large-scale process, and that still is somewhat mysterious, but it's direct evidence here that the small scales can never do that.
Of course, I mean, small-scale dynamo doesn't create a large-scale flux imbalance. That is what you need for the sunspot cycle.
Well, there are people in the community who thought otherwise. Then the second piece that I find significant is, I think it was like 23 years ago that Cattaneo came up with these simulations, and he didn't have an energy equation in his simulation. They were pure MHD simulations at the time, where he predicted that the field structures would be shredded into these very, very narrow sheets. And in your simulations, where now the thermodynamics are about as good as one can do it, or probably as one needs to do it, still this sheet-like structure has prevailed, which brings me to the question, at what resolution would we see these very small sheet-like scales?
I mean, even with DKIST, you might see some indications. I mean, if you look right now in quiet sun observations, most features look like more or less roundish flux tube-like features, but the round thing you see is a point spread function of your telescope. I think with DKIST, you should be able to see that this roundish feature becomes elongated in some direction, which is likely correlated with the direction in which the downflow lane expands. So,
Also.
You commented that when you don't have a magnetic field, the edges of the granules are more ragged,
yeah,
presumably on a very small scale.
yes.
Can you comment on how that influences the structure of the optical spectral lines?
Not very much, as far as I know. We did some analysis where we looked actually at how the magnetic field, the small-scale magnetic field, influences oxygen and iron abundances. And to this end, we compared the hydro to a dynamo snapshot. And the differences we found is very small compared to the recently suggested abundance changes. So it's likely really a higher order effect.
Comforting.
I found it's interesting at the beginning you draw the similarity between the particle distance and B, but particle distance doesn't have any implication for energy. But
No,
B does,
it's
right?
just to point out that basically on a fundamental level, the chaotic property of a velocity field leads to an exponential growth of this equation, which determines the time evolution of the separation of nearby streamlines. And since an induction equation is mathematically identical to that equation, if you have a chaotic velocity field and you sprinkle in a weak magnetic seed field, you also expect the exponential growth of the magnetic field. That was the analogy I wanted to point out there.
And the energy of the B energy comes from the conversion from
It becomes mostly initially from the stretching term, but as the magnetic field becomes stronger, it then at some point changes the velocity field in a very convolved way. I mean, it doesn't suppress the shear too much, but it kind of misaligns the direction of the field with the direction of the shear, so that the overall energy which is converted through the Lorentz force and the shear term is reduced. But it's really about the relation of the magnetic field to the velocity field. And this is also something I think Stephen Tobias and Fausto Cattaneo pointed out. If you take the velocity field from a saturated dynamo and run another kinematic dynamo simulation with that velocity field, it's still a very efficient dynamo. The saturation is not a property of the velocity field. It's about the magnetic field relative to the velocity field.
Question?
You've raised many interesting issues. One of them is the great competition between the small-scale dynamo and the large one. They're likely not operating quite the same places. In fact, your simulations are carried out with no shear.
Yeah.
Even if there's a near-surface shear layer, it may not play a big role. On the other hand, we suspect that the global dynamos very much are influenced by strong rotational constraints. They may be running small-scale stuff at the same time. So although the Fausto Cattaneo and Steve Tobias paper has things competing, but they have it competing in the same place. The sun may continue with its doing different things in rather different places.
Yeah, I mean, as long as the flow is chaotic throughout the convection zone, the small-scale dynamo is likely everywhere. In that sense, no matter where the large-scale dynamo is, it will find a small-scale dynamo there too. But, I mean, it's an open question, but I just want to point it out here that it appears from extrapolating these results that these small-scale dynamos tend to be maximally efficient and they take all the resources they can get. And energetically, that might put some constraints on the operation of a large-scale dynamo in addition. It's not that simple that you just add another powerful dynamo to it. There needs to be some competition.
But just below the surface, you have very strong driving on very small scales.
Yeah, but actually, I mean, Hideyuki has done these small-scale dynamo simulations throughout the entire convection zone. I think he gives a talk tomorrow about them, right, at CU, and another colloquium talk here. But he looked at what they do if you really use the same approach, but you use the whole convection zone. And the magnetic field is strongest also in the deeper parts of the convection zone. It's not that the photosphere is, it has the shortest time scales, but in the deeper convection zone, you have also more energy available. So he finds close to equipartition down there. The convective arm S velocity gets reduced by almost a factor of 2 due to the Lorentz force feedback. So it shapes convective motions and has an influence there.
Now, I think all of us hope that the remaining puzzle will be solved by getting detailed information about realizations of dynamos on other stars that have other extents of convection zones, other rotational speeds and the like. And I would presume from what you presented that the small scale dynamo picture would only change very gradually, whereas the large scale dynamo, depending on these issues like rotation, extent of the convection zone, will then change the ratio between the two. And so at what point would you expect we can then find a critical change in the interplay between the two?
And that's a question which goes far beyond what I looked at, since I really looked at it only from the perspective of a small-scale dynamo. And it's a good question, energetic. What I showed here, it's likely that the small-scale dynamo takes close to all the resources available. It's a good question. How large is the part of that resource which could be taken by the large-scale dynamo? I don't know what the answer is. And it's also very difficult to actually draw the line. Starting from which scale is it a large-scale dynamo? You cannot get a large-scale dynamo without having some magnetic energy in the small scales. What you can look at is maybe what is the energy converted by the large-scale shear flow. At least in the case of the sun, that seems to be most probably 2 orders of magnitude less than the energy converted by the small-scale dynamo. But how much different that could be in other stars, I don't know.
This work is clearly way above my pay grade, but how important is reconnection in all of this?
It's very important. You cannot have a dynamo without reconnection, since you would just get topological constraints, which sooner or later will just kill it. So in some sense, you don't want to have too much magnetic diffusivity. You want to have your magnetic Reynolds number high enough, but you don't want to set the diffusivity to 0 either.
And not really a related question, but you showed in the quiet sun simulations that the bright points that appear in the intergranular lanes were more a sort of a transitory effect of the field. Now, if you go into a plage region where the field concentration is higher, would you expect basically the same transitory?
No, there you have much longer lived strong field concentrations, and I mean, they stay there for much longer. Basically, I mean, the network then evolves over a time scale. If it's a mesogranular network of mesogranulation, if it's supragranular network, so you have something for several hours there. It's not really on the scale of minutes or so.
Okay, no more questions. Thank you, Matthias, again, for an excellent talk.